Good morning, everyone. Hello.
Good morning.
Good morning. So if you are able to open your camera and say good morning to the classmate, you can do it. And then you can close it if you want. So no one would like to say good morning to his classmates or her classmates?
Good morning.
Good morning.
Good morning.
Good morning.
Good morning.
Good morning. Good morning.
Good morning.
Good morning.
Okay, guys, because there are some issue in our classroom, so it is more safe to move to Zoom until they fix the problem. I think there is some issue with the COT or something. I'm not expert in these kind of things, but your save is much better. So this is why we moved to Zoom until they fix the problem. Okay, so I will go over the lecture notes today online. And if you have any question at any time, you can stop and unmute yourself and ask me the question at any time. Okay? Any question before I start? Any questions before I start? I'm planning to finish chapter 2 today. We have some slides haven't finished in lecture note number 1, chapter 2, and we're gonna cover the part 2 in chapter 2. Okay. Any questions again before I start? Nice to see you online. Okay. But you close your camera, so it looks like I'm talking to my computer, but it's fine. It's okay. I'm sure you are there. Okay. Don't leave your computer and go someplace. Okay. So let me set up my computer. I will write on the screen. Let me share the slides. And let's see where we stopped last time. So as I said, there is no homework this week, and let's see where we stopped on this lecture note. We covered the first case, which is sigma 1 square equals sigma 2 square. This is assumption about the two variances of the two population or the two treatments we are working with. And then we stopped at the confidence interval for mu1 minus mu2. Sometimes we are not interested in mu1 equal mu2 against mu1 greater than or less than or doesn't equal mu2. Sometimes we are interested in the difference is what? So the difference between the two treatment averages or the two treatment means is between what two values? So we are interested in lower limit and upper limit of the difference of some parameter, which is in this case mu1 minus mu2, is between what two values? So the confidence interval in general for the difference between two population means or two treatment means, it is y1 dot bar minus y2 dot bar plus or minus some value from the t-distribution table at alpha over 2 and the degree of freedom, which is n1 plus n2 minus 2 times, because you assume equal variances. You assume sigma 1 equals sigma 2 or sigma 1 square equals sigma 2 square. you estimate only one standard deviation. We called it pooled standard deviation times the square root of 1 divided by n1 plus 1 divided by n2. Do I have all these numbers? We have all these numbers. We have n1 is 5, n2 is 6. We calculated SPB4, and we have 1 dot bar, y2 dot bar. The only thing left, or the only thing we don't know, is t value. To find the t value, you need to find alpha over 2 and n1 plus n2 minus 2. So you can go to the t distribution and find the t value from the t distribution at alpha over 2. Alpha is 5%. 5% divided by 2 is 0.025. And degree of freedom n1 plus n2 minus 2. So 5 plus 6 minus 2 is 9. So you go to the table and find this t value and plug in the equation. So let's go to the t value. I already uploaded the t distribution table on Canvas. So let me show you this one. Under statistical tables, and this is the standard normal distribution table and the t distribution. The first 2 pages are for the standard normal distribution. The last page is in t distribution. The degree of freedom, our degree of freedom is 6 plus 5 minus 2 is 9. So this is 9, but there are many t values. We need the one which is at alpha over 2 is 0.025. So this is 0.025 and 9. So this is our t value for the confidence interval. Alpha over 2 is 0.025 and degree of freedom is 9. So it's 2.262. So let's go to these slides. So now I have everything. Plug in all these values. This one minus give me lower limit. This one plus give me the upper limit. So plug in all these values. Do I have all these values again? As I said, this one is n1. This one is n2. This one is y1 dot bar. This one is y2 dot bar. This one is s square 1. This one is s square 2. And this one is S1, this one is S2. So I plug in all these values, I plug in N1, N2, and I calculated SPB4, and plug in T, plug in Y1 dot bar, Y2 dot bar, you get lower limit is negative 10.31, upper limit is 6.65. What does it mean? It means if we did the experiment on a very long scale, like selected many plants as you assigned to the first treatment or the first fertilizer, and I assigned many plants to the second fertilizer, and I calculated mu1 and mu2, and then I calculated the difference mu1 minus mu2, it will be some value between these two values at significant confidence level 95%. Can I use this confidence interval to test H0 mu1 equal mu2 against H1 mu1 doesn't equal mu2? Can I do the test using the confidence interval? You can do it. How it comes? Because this one can be written as mu1 minus mu2 is 0. And this one can be written as mu1 minus mu2 is not 0. So this confidence interval, the lower limit is negative, upper limit is positive. 0 is one of the possible values, 0 in the confidence interval. So we fail to reject H0. So how, in general, how do I use the confidence interval to do test of hypothesis? If the lower limit is positive, upper limit is positive, you conclude that mu1 is greater than mu2. It means you reject H0. If the lower limit is negative, upper limit is negative, you conclude that mu1 is less than mu2. So they are not equal. So you reject H0. If the lower limit is negative, upper limit is positive, you conclude that mu1 equal mu2. So you fail to reject H0. This is in general. For our confidence interval, lower limit is negative, upper limit is positive. So we fail to reject H0. It means the two fertilizers are the same in terms of yield at confidence level 95 or significance level 5%. Because if the confidence level is 95, the significance level for testing is 5%, the complement. Do you have any question about the confidence interval for the difference between two population means or the two treatment means? Okay. So how do I do the t-test? How do I do testing using R? Now we did it by hand, but how do I use R to do the test? Use a function called t.test. You give this function the first group of data, the second group of data, yield A, we save the 5 values in yield A, we save the 6 values, yield B. So I gave it the first column of data, second column of data, or first group of data, second group of data, and we assume the sigma 1 equals sigma 2 square. This assumption is very important. So we need to give R function or t-test function the assumption about sigma 1 square and sigma 2 square. They are equal or they are not equal. We still work with this case that they are equal. This one, sigma 1 square equals sigma 2 square. So when I gave the R function, that assumption, it gave me the same results we got by hand. This is the T0. This is the degree of freedom. This is the p-value. And he said the alternative hypothesis is the true difference in means is not equal to 0. It means the alternative H1 or HA, sometimes you write HA, mu1 minus mu2 is not 0. And this is the lower limit of the confidence interval, 95%. This is the upper limit of the confidence interval, 95%. This one is Y1 dot bar. This one is the average of the second treatment or the second fertilizer, Y2 dot bar. So you use the t dot test function to get the confidence interval and do the test of hypothesis. But you need to give this function the assumption about variances. Sigma 1, you assume sigma 1 square equals sigma 2 square, or you assume sigma 1 square doesn't equal sigma 2 square. So this is how do I do it by R. So let's cover the second case, which is sigma 1 square doesn't equal sigma 2 square, and see what will it change. Guys, if you have any question, at any time, stop me, unmute yourself, and ask me the question at any time. So if you do not have any question, let's go over the second case, which is sigma 1 square doesn't equal sigma 2 square, and see what will it change. The test statistic value, will it change or not? The decision, will it change or not? And what else will it change based on the assumption? Now, the second case, unequal variances, sigma 1 square doesn't equal sigma 2 square. The statistical model is the same. I is 1 and 2, two fertilizers. J is from 1 up to Ni. N1 is 5, N2 is 6. But the assumption about epsilons will be different. See, now I change it sigma square to be sigma I square. So it means we have two sigmas, two different sigmas. Sigma 1 square, the variability for the first fertilizer, and sigma 2 square, the variability of the second fertilizer, and we assume they are not equal. This is why I change it epsilon ij follows normal with mean 0 and sigma square to be sigma I square. This is the only difference in the statistical model. And let's look at the first step. First step, nothing changed. Second step, alpha is 5%, doesn't change. The third step will change, because now we do not have SP, the pooled standard deviation. We have two different standard deviation or two different variances. So T0 equal Y1 dot bar minus Y2 dot bar divided by square root of S1 squared divided by N1 plus S2 divided by S2 squared divided by N2. But I have all these values. So I can calculate the T0 and then calculate p-value and then take a decision. Another something we need to change is the degree of freedom. The degree of freedom in the first case, when you assume sigma 1 square equal to sigma 2 square, the degree of freedom is n1 plus n2 minus 2. But if you assume sigma 1 square doesn't equal sigma 2 square, this degree of freedom doesn't work. There is some guy, his name is Satterthwaite, I think, came up with this formula and said this formula for the degree of freedom is much, much better than this formula when you assume sigma 1 square doesn't equal sigma 2 square. And this degree of freedom, or nu, it is a function of S1 square, S2 square, N1, N2. And I know it is very big, but it's very nice. If you divide it from the middle, it is symmetric. The left-hand side is for S1 for 1, right-hand side for 2. So you need to calculate the degree of freedom using this formula. If you assume sigma 1 square doesn't equal sigma 2 square, and then you go to the t distribution table to find the t value for the confidence interval and use this degree of freedom to find the p-value for testing. So let's go over the 5 steps. The first step, mu1 equal mu2, the two fertilizers are the same in terms of the yield. Against H1, mu1 doesn't equal mu2, they are not equal in terms of the yield. Can I make this one greater than or less than? You can do it because it is based on the research hypothesis you have. Maybe you as a researcher, you would like to test mu1 greater than mu2, or you would like to test mu1 less than mu2, or you test mu1 doesn't equal mu2. What it changed based on this one? The only change is the p-value. When you calculate the p-value using the applet, you need to give this information to the applet. It is greater than or less than or doesn't equal. The second step is the same. Alpha is 5%. Third step, this is the formula. Plug in y1 dot bar 20.7. Plug in y2 dot bar is 22.53. Divided by the square root of S1 square is 49.43 divided by 5. Plus S2 square is 29.51 divided by 6. And we got T0 as negative 0.48. So I can use this one with the degree of freedom. And the alternative doesn't equal to find the p-value. So I need to find the degree of freedom before I calculate p-value. Because when I go to the applet will ask me, what is your T0? I know my T0 is negative 0.48. And it will ask me, what is the degree of freedom? And what is the alternative sign is what? The alternative is greater than or less than or doesn't equal. It is doesn't equal. But the degree of freedom, I plug in all the values. And I got 7.49. Should I round it to be 8? You should round it down all the time because it is more safe to work with a smaller degree of freedom. So this is why I round it down to be 7. Even if it is 7.6, I will make it 7. So the degree of freedom is 7, and the alternative is doesn't equal. Now let's go to the applet and find the p-value. Can I use the t distribution table to find the p-value? Sometimes it works, sometimes it doesn't work. But the problem with the t distribution table, when I use it to find the p-value, it gave me a range of values for the p-value. It doesn't give me an exact value for p-value. This is why we should use some software. We should use some applet on the internet, or you can use R. So let's practice on this little applet first. The nu is the degree of freedom. Degree of freedom is 7. X is the T0. T0 is negative 0.48. And then the alternative is doesn't equal. I selected the third one. This is our p-value. It's still big, 0.64586. Oh, did you see? I didn't share this one. Let me share it. See, I gave the degree of freedom 7. So guys, when I explain something and you do not see it, please let me know, okay? So the degree of freedom is 7. T0 is negative 0.48, and the alternative is doesn't equal. Use this one if it is greater than, use this one if it is less than, use this one if it doesn't equal. So the degree of freedom, why it doesn't give me, let me give it again. Negative 0.48, and this one is doesn't equal. So this is the p-value, 0.64, still big. So when I assume sigma 1 square equals sigma 2 square, I failed to reject H0. When I change the sigma 1 square doesn't equal sigma 2 square, I still fail to reject H0. But sometimes it changes. So let's go out to our slides again. So now the p-value is 0.645. Now I take my decision. The p-value is very big compared to significance level 5%. So there is no enough evidence to reject the null hypothesis. This means a standard fertilizer mixture and the improved one are almost the same or the same at significance level 5%. When we assume difference population, but you should say at 5%, the significance level always should be mentioned. Because sometimes if I change its significance level, the decision will change. Any question about testing when we assume sigma 1 square doesn't equal sigma 2 square? Okay. So what if I'm interested in confidence interval? What is the confidence interval of mu1 minus mu2 if we assume variances are not equal and calculated for the tomato experiment? Let me write down the confidence interval when we assume sigma 1 square doesn't equal sigma 2 square. When you assume sigma 1 square, sigma 1 square doesn't equal sigma 2 square, the confidence interval will be what? y1 dot bar minus y2 dot bar. It is the same as before, plus or minus t at alpha over 2, and the degree of freedom, keep in your mind the degree of freedom this time is 7. We already calculated this one, times square root s1 squared divided by n1 plus s2 squared divided by n2. Do I have all these values? You have all these values except t. So I need t value at alpha over 2, 0.025 as before, and 7, not 9. Because when I assume sigma 1 square equals sigma 2 square, the degree of freedom was 5 plus 6 minus 2. When you go to the table and you choose the one at degree of freedom 7, you will find it is 2.365. So now I have everything. Let's plug in these values. y1 dot bar is 20.7 minus y2 dot bar 22.53 plus or minus the t value is 2.365 times the square root s1 square is 49.42 divided by 5 plus s2 square is 29.51 divided by 6. When you calculate this one minus this one, give me the lower limit negative 10.93. This one plus this one, it gave me upper limit 7.26. Still lower limit is negative, upper limit is positive. So we conclude that mu1 equal mu2. It is the same conclusion. So we fail to reject H0 at significance level 5%. But if you would like to explain the confidence interval, you should say with 95% confidence level, the difference between the two fertilizers in terms of the average yield is between negative 10.93 and 7.26. This is the meaning of the confidence interval. With 95% confidence level, the difference between the two population means, the two treatment means, the two fertilizers means, mu1 minus mu2. That difference is between negative 10.93 and 7.26 with confidence level 95. Any question? Okay, so how do I get the confidence interval using the t-test function? Assuming sigma 1 square doesn't equal sigma 2 square. So you should make variance equal false. This is an option. So you use the t-test again. You give the first group of data, second group of data, and you comma, and then you give variance equal. That assumption is false. It means sigma 1 square doesn't equal sigma 2 square. And it gave you the t-value, gave you the degree of freedom is 7.48, approximately 7, p-value is 0.6, and the alternative hypothesis is the difference is not equal 0, and this is the lower limit of the 95% confidence interval. This is the upper limit of the 95% confidence interval. This is y1 dot bar, this is y2 dot bar. The sample mean of the first fertilizer, the sample mean of the second fertilizer. So what is the rule of thumb for equal variances? Let me remind you. How do I decide that equal variance is false or true? There is a rule of thumb we covered, but there is a test I will cover in a few minutes. The rule of thumb is S maximum, the biggest standard deviation, divided by the smallest standard deviation. If this one is less than 2, or S square maximum, the variance, the bigger variance, divided by the smaller variance, is less than 4. If this one is satisfied or this one is satisfied, you assume sigma 1 square equals sigma 2 square. Otherwise, you assume sigma 1 square doesn't equal sigma 2 square. But I will show you a test, because there is a test. It's better than rule of thumb. So now let's look at the, go ahead. Yeah, sure.
For the example that you did, you said where the variances weren't equal. You had put that they were equal, but before the slide before this one.
Okay, this one is variance equal, false,
No,
means
the
sigma 1 square. This one?
One before this one. Yeah, you said
Thank you so much.
It's not equal. Is that
Not
what you-
equal, yeah.
Okay. Okay.
Any other mistakes? Please, if you see any mistakes, let me know. Thank you so much. Any other questions? Okay. So now let's check the assumptions. The assumptions are, for the t-test, the two samples are independent. We have a group of plants assigned to the first fertilizers. They are 5. They are completely different from the other group, which is 6 plants. So the 5 plants is not the 6 plants. They are different. So this is why we call it two samples. Can be the same, can be the same. We will cover this one in lecture note number 2 in a few minutes. The second assumption is the two samples are randomly selected from normal distribution. So each sample should be follows normal distribution. So I need to check normality for each group of data. The first group of data has 5 values. Second group of data has 6 values. I need to make sure the normality is satisfied. Keep in your mind, we looked at the histograms, but the histogram doesn't work because the sample size is small. So we need to look at something better, which is normal probability plot. So let's check the normal probability plot and also do a test, which is Shapiro test, to make sure normality is satisfied or not. Otherwise, I shouldn't conclude that they are equal, because actually we should look at the assumptions before we make any conclusions. Because in this one, we concluded that they are equal. Before also, we concluded they are equal. But all these conclusions are based on the assumption normality. So we need to check normality. So how do I check normality? You can use a function QQ norm, and you give the first group of data. And then QQ norm gives the second group of data. Oh, this one should be B. Come on. And then I will write something called the QQ line. Let me show you. Oh, they are exactly the same. I should make this one B, this one B. Sorry, guys. But I hope that I did the Shapiro test with A and B. This is why they are exactly the same. But I will change this one and update the lecture note. So this one is A, and this one is also A. So let's look at this one. How do I know from the QQ plot that the assumption is satisfied? If the dots are making a straight line, these points are making a straight line, it means the normality is satisfied. Why? Because actually in this QQ plot, it compares the actual data you have with the normal data. This is your data, and this is the standard normal data. If I graph something like scatter plot between the data and the standard normal data, and I found there is a straight line, it means it matches the normal data. So this one means normality is satisfied, but this one should be for B. Normality also, by the way, is satisfied. So you use the QQ norm to get these dots, and you QQ line to give me the straight line to see if they are close to the straight line or not. So I use QQ norm for A, and I should use QQ norm for B to B, and then QQ line for A, QQ line for B. And this one only to get the two graphs in only one, the two plots are only in one panel, but you don't need to use this one. But I will go over this one in details when I cover the R code after we finish chapter 2. So let's look at the Shapiro test, because normality looks like fine from the QQ plot. Let's look at Shapiro test. Shapiro test function is what? Shapiro.test, and gave the first group of data. Shapiro.test gave the second group of data. I'm happy that I didn't make them AA, because the test is more formal compared to a graph. So let's understand the Shapiro test. Shapiro test gave me a p-value, I need this p-value to be big to assume normality is satisfied. Why? You need to be familiar with H0 and H1 for Shapiro test. H0, H1 for Shapiro test. H0 is always normality is satisfied. HA is always normality is not satisfied. So normality is satisfied. Normality is not satisfied. For our case, normality is satisfied for A, normality satisfied for B, normality is not satisfied, not satisfied. So p-value should be big to fail to reject H0. My p-value is greater than 5%. So we conclude that, or we fail to reject H0. So normality is satisfied to the first group of data, or the first fertilizer. Actually, the same thing for the other one, because p-value is always big. So p-value greater than 5%. So we fail to reject H0. So normality is satisfied. So the assumption is satisfied. So our conclusion is fine. So now we can say that the two fertilizers are the same in terms of the average yield at significance level 5%, because the assumption of our data are satisfied. Any questions so far? So this is always the null hypothesis and the alternative hypothesis for Shapiro test. And this is the R code. You should use Shapiro.test, between brackets, give the data, first data set, first data set, or the first group of data, second group of data. So normality assumption is satisfied. So we cover two cases, equal variances and unequal variances. We use the rule of thumb to decide, but we have a test for equal variances. I know we use the rule of thumb is easy, but we should do a test. It's better than rule of thumb. So what is the name of that test in R? Or what is the name of that function? The function is var.test. var.test, variance testing for variance. You give the first group of data, second group of data, done. This one shouldn't, I shouldn't give this comma. This one is typo, this one is error. So, and you save under some name, you give any name, and then you print what is saved under this name, it gives you this output. So the function to test equal variances is R is var.test. By the way, anything we use in chapter one will be used in chapter 2, chapter 3. So even if you didn't get the idea of the test this time, like var.test, we're gonna repeat it one more time, and so on. So var.test is a function can be used to test equal variances, because we practiced on sigma 1 square equals sigma 2 square. And also sigma 1 square doesn't equal sigma 2 square, but we need to know which one is correct. Based on the rule of thumb, this one is correct. But now based on the test, this is much better than rule of thumb. For the test comparing two variances, it gave me the nominator degree freedom, denominator degree freedom, but the ones I'm interested in is this value. He said the alternative hypothesis, true ratio of variances is not equal to 1. What do you mean ratio? We didn't talk about ratio. We use H0, sigma 1 square equals sigma 2 square versus H1. Sigma 1 square doesn't equal sigma 2 square. This is what I'm going to test. This one can be written as H0, sigma 1 square divided by sigma 2 square equal 1. Again, is sigma 1 square divided by sigma 2 square doesn't equal 1. So R use this format, not this format, the first format. So the alternative, the true ratio of variances is not equal to 1. It means sigma 1 square doesn't equal sigma 2 square. But the null hypothesis is always equal. So I should look at the p-value, and my p-value is very big. So p-value greater than alpha, which is 5%. So we fail to reject H0. It means that we can conclude sigma 1 square equals sigma 2 square at 5% significance level. So we should go with the conclusion in the case that sigma 1 square equals sigma 2 square. I know we practice on both just for practice, but if they have different conclusions, you should go with the conclusion of sigma 1 square equals sigma 2 square case. Any questions so far? Any questions so far? Okay. So if you do not have any questions, let's go to the lecture note number 2. Let's cover if these two samples are dependent, because we covered in this lecture note the two samples are independent. So let's cover the second case. Keep this one. And let's okay. Let me share the second slides. Open part 2. Let's share part 2. Let me So this is part 2. Pair the t-test, and then it checks the assumptions again, because we need to know the assumptions are the same or different. The idea is, when in the part 1, we worked with 2 independent samples. The first sample were 5 plants. Second sample are 6 plants. The 6 plants are different from the 5 plants. Can be the same, can be the same. Sometimes I have only one sample, but I measured it twice. So every individual or every experimental units measured twice. Like, for example, I selected 10 persons, and then I measured the blood pressure of each person, and then I gave some kind of medicine, and then I measured the blood pressure again. Now I have 2 groups of data, but the 2 groups of data comes from the same people, from the same sample, because each individual or each participant or each experimental unit measured it twice. In this case, the 2 groups of data are dependent because they come from the same individuals, but it's different from the independent case. So let me give you some example. I give you 1 minute to read it very quick, and I will go over it with you again. So please read this one. Okay. Consider a harness testing machine that presses a rod with a pointed tip into a metal specimen with a known force. By measuring the depth of the depression caused by the tip, the hardness of the specimen is determined. 2 different tips are available for this machine. The 2 tips are the 2 treatments. Those are the 2 tips. We need to know which one is harder. And we have some experimental units, like some specimen. And we can do this experiment as the one we covered, like complete randomized design with 2 independent samples. And I can make as a paired experiment, or do paired t-tests or paired comparisons. So let me talk about these 2 cases. So one of the possible ways to see the 2 tips are different or not, you can select a number of metal specimen, let's say 20, and these 20 could be randomly assigned to the 2 tips, randomly assigned 10 for the first specimen and 10 for the second specimen. 10 for the first tip and 10 for the second tip. And this one would be completely randomized design. So the average hardness of the 2 steps could be compared using the t-tests that we covered. In this case, if this design, like the one we covered in part 1, we have 2 independent samples. The 10 specimen assigned to the first tab will be completely different from the 10 assigned to second tab. But there is a problem here, because maybe the specimens are different in terms of hardness. So suppose a metal specimen were cut from different power stock that were produced in different heats that might affect the hardness. This lack of homogeneity between a specimen will contribute to the variability of the hardness measurements and will tend to inflate the experimental error. It will make sigma square very big. It will make sigma square, or the experimental error, very big, because some variability due to different types, and some variability is due to the difference between a specimen. So the variability due to different specimens, or the different hardness for these specimen, will add more variability to the experimental error. So we need to take some variability due to the specimen, and the remaining variability will be used to test the difference between the tips. thus making a true difference between the tip harder to detect. So to protect against this possibility, assume that each specimen is large enough so that two hardness determination may be made on it. Then randomly assigning one tip to one half of each specimen and the other tip to the remaining half. What do you mean? I mean, there are two ways again. Let me explain it again. There are two ways to do the experiment. One of them is better than the other, like tip 1, tip 2. I can assign some specimen to this one, like 10 specimen to this one, and 10 specimen to this one. And this 10 is different from this 10. This 10 is different from this 10. So two independent sums. And I compare the two tips in terms of the average. But this one is not good because the tips may be different in terms of hardness. So it will add more variability to the experimental error. So a better way is what? Tip 1, I will use the 20 tips. Tip 2, I will divide each tip into 2 parts and randomly assign a tip to each part. Like maybe this one received tip 2, this one received tip 1. And the other one also will be divided into 2. Maybe this one will receive tip 1 and this one receive tip 2. The third one maybe I divide into 2 parts and randomly assign the 2 tips, maybe T1, T2. To the last one, number 20. So I will use the 20 specimen. And each will be used to test the 2 tips, maybe T1, T2, randomly assigned. So I will have a number from this one, 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 number from this one. So I will have 2 groups of numbers, but the 2 groups are dependent, not independent, because each 2 numbers, each pair of numbers comes from the same tip. So in this case, 7 and 6 comes from the first specimen. 3 and 3 comes of second specimen. To the last one comes from the number 10. Let's use 10. In this case, we use 10, not 20. In this case, this group of data is dependent from this group of data. I cannot work with them as dependent. So what should I do? You calculate something called difference. You work with the difference, like 7 minus 6 is 1. 3 minus 3 is 0. To the last one, 4 minus 5 is minus 1. So you work with this group of data. Do not work with the tip 1, tip 2. And then we can do the test using this D. So let's see the statistical model, will it change or not, and anything else will it change. Yij equal mu I, the average of each specimen, average of each tab. So mu1 is the average of first tab, mu2 is the average of second tab. But we added something to the model. This is the specimen effect. Looks like each specimen is a block. And within each block, we test all the treatments. We have only 2 treatments. I is 1 and 2, J is 1 up to 10, is not Ni, because for each, we have the same number of values. J is from 1 to 10. Epsilon Ij follows normal with mean 0 and sigma I squared. And I is 1 and 2. And we are going to work with the difference dj, dj is y1j minus y2j, and j is from 1 to 10. So we are going to calculate 10 differences. And the assumption actually is not on the epsilons. The assumption is on the differences. These differences should follow normal distribution with mean 0 and equal variance sigma squared. So we are going to test the assumption for D, not first group of data or second group of data. The differences should follow normal distribution. And to make sure that DI is unbiased estimator for the difference between the 2 treatment means or the 2 tips means, we calculate the expected value of DI is the expected value of y1j minus y2j it is equal the expected value of y1j minus expected value of y2j. The expected value of y1j is mu1 plus beta j, and the expected value of y2j is mu2 plus beta j, whereas epsilons, the expected value of epsilons are zeros. And this one will cancel this one. So the expected value of the difference is mu1 minus mu2. So when we work with mu d, we already work with mu1 minus mu2. So we can test mu d is 0 against mu d doesn't equal 0. It will be the same hypothesis as we worked before. So let's go over the 5 steps for the pair dt test. The null and the alternative. The null is the difference is 0. Keep in your mind the difference is 0. It means the two tips are the same. Against the difference is not 0. It means the two tips are different. Or you can use as mu d greater than 0 or mu d less than 0. It's up to you. Or based on what you are interested in as a researcher. The significance level as before, let's use 5%. Third step, calculate the T0 test statistic value. Test statistic value is D bar, the average of differences, divided by SD, the standard deviation of the differences, divided by square root of n. So what is D bar? D bar is the sum of the differences divided by n. What is SD? It is the same formula for the standard deviation. The formula is 1 divided by n minus 1 times the one you memorize is the sum of x squared, so it will be the sum of d squared minus the sum of x all squared, it will be the sum of d all squared divided by n. So it is the same formula for the standard deviation, but you change x to be d. So we need sum of d, we need sum of d squared, we need n to be able to calculate d bar and sd. And to calculate p-value, use the same applet, and then you take a decision. So let's practice on this one. Any questions so far? Guys, any questions so far? Okay, so let's follow these steps. This is the tab 1 value. This is a tab 2 value. I'm not going to work with these two groups of data. I'm going to work with the difference. And this negative one is the sum of d. I need this number to calculate d bar. And I need d square, u square. 1 times 1 is 1. 0 times 0 is 0. Negative 2 times negative 2 is 4. Times 1 times 1 is 1. To the last one, negative 1 times negative 1 is 1. The sum is 13. This one is the sum of d square. I can use these two values to calculate the average. D bar is sum of d divided by n. So negative 1 divided by 10 is negative 0.10. I can use these values to calculate the SD. You plug in sum of d squared is 13, sum of d is negative 1, and n is 10. You get the standard deviation of the difference is 1.197. I need these two values to follow the 5 steps. So let's follow the 5 steps. The first step is H0. Mu of the difference is 0. The two tips are the same. Against mu of the difference is not 0. They are not the same, but you can use one of them is greater than the other. It's up to you. Second step is alpha. Let's use 5%. Third step is T0. It is d bar divided by SP divided by square root of n. D bar is negative 0.10 divided by negative 0.010 by negative 0.10 divided by the standard deviation of the differences. Oh, this one SD. SD is 1.197 divided by square root of n square root of 10. This t value is negative 0.26. Why I need this value? I need this value to calculate the p-value. How do I calculate the p-value? Let's go use the applet because the table is not good. Before I go to the applet, I need T0. it is negative 0.26. I need degree of freedom. What is the degree of freedom in this case? The degree of freedom is very simple. How many pairs minus 1? So it is 10 minus 1, it is 9. The last step, the last information I need is H1 is what? H1 is doesn't equal. So now let's go to the applet and find the p-value. You give the applet negative 0.26, degree of freedom is 9, the alternative is doesn't equal, and then I calculate the p-value. So let's go to the applet. Where is the link for the applet? This one. So let me share, be able to see it. Guys, do you see the screen? Do you see the T distribution screen?
Yes.
Okay, thank you. So the degree of freedom is 9. And the T value or T0 value, which is X in the applet, is negative 0.26, negative 0.26, and the alternative is doesn't equal. So this is the p-value, 0.8. So now let's go to the slides. So now we have here p-value is 0.8, 0.8. The p-value is very big, so let's take a decision. The p-value is greater than alpha. So we fail to reject H0, or there is no enough evidence to reject H0. So we conclude that the two tips are the same in hardness at 5% significance level. You have to say 5% significance level, because if you change the significance level, maybe the decision will change. So this is how to do the t-test for the paired experiment or the dependent two samples. So how do I do the paired DT test? Using R. Use the same function again, to t dot test. So the function t dot test can be used to test mu1 equal mu2 for the independent case, and mu d is equal 0 or not for the dependent case. And also for the first case, the two independent samples, you can use it for the equal variances or unequal variances. So in this, now I give you the syntax of the function, like t-test, you give x, you give y, you give the alternative is what, because you can change it, the mu is what, the paired is false or not, equal variance is false or not, confidence interval, you can change it, and there are many other options. So let's run R. So I gave the tab 1 some values. I use the function C colon. I gave those values, 10 values. I gave tab 2 values, use the function C. And then I said t-test, gave the first group of data, second group of data, and R will calculate the difference and do all the other job. So, and the alternative is two-sided, but if I didn't give the two-sided, it will be considered doesn't equal. And the paired is true. Now I tell R that you shouldn't work with these two groups of data. You should calculate the differences and work with the differences. And then I print what I saved, and it gave me this is T0, and gave me this degree of freedom. It gave me the p-value is 0.8, almost 0.8, and the alternative is the difference is not 0. So H0, H1, mu d is not 0. I can change it if I want, greater than or less than. And give me also 95% confidence interval, but we haven't calculated this one. But it gave me lower limit for the mu d, upper limit of mu d. So mu d is between these two values, negative 0.956 0.756. Can I use this one to do a test? Yeah, because the lower limit is negative, upper limit is positive, you fail to reject H0. So, and this is the estimation of mu D, which is D bar. So the conclusion is the two tips are the same at significance level, 5%. Any question so far? Any question? Okay. As I said, the assumption in the dependent case is not on X's, it's not on the two groups. It is on the differences between the two groups. The differences follows normal distribution. So I need to check normality for the differences, is not for the first for the first group, second group, as we did in the two independent cases. So the histogram for the differences doesn't work because we have only 10 values. So I cannot tell it is normally distributed or not because we have only 10 values. So this one doesn't work because the sample size is small. And the box plot looks like normality is satisfied. The two boxes are very close to each other. So I think normality is satisfied, but it's better to look at the QQ plot, and it's much better to look at the formal test. So this one, if the sample is very big, is fine. It gave you the same conclusion of this one, the same conclusion of QQ plot and the test, but the sample size is small, do not depend on the graphs. But if you like to look at the graph, you look at the QQ plot, looks like making a straight line, but there are some values far away from the straight line. So I cannot tell from the graphs that normality is satisfied. Looks like I need to do a test. So let's do a test. Shapiro test. P-value is small. I reject H0. So H0, normality is satisfied for the differences. Again, is normality is not satisfied. This p-value less than alpha, less than 5%. So we reject H0. It means normality is not satisfied. Normality is not satisfied. So I shouldn't conclude that the two tips are the same. I shouldn't conclude the two tips are the same. I need to fix the problem first. So as a researcher, I shouldn't look at these conclusions because the assumption is not satisfied. So what should I do? There are many ways to fix the problem. Like you can find some transformation for the data to make the normality satisfied. I will show you later how to fix this problem. If normality is not satisfied, I will show you later how to fix the normality assumption if it is not satisfied, because we need it to be satisfied to keep working with parametric tests, which has big power compared to the non-parametric tests. But if you couldn't fix the problem, if you couldn't fix the normality problem, you have to go to non-parametric tests. So I will cover this idea how to fix the normality and these kind of things later. So paired comparison t-test is a special case of the complete randomized block design that will be covered in chapter 4 in details. I will post a ungraded quiz about the chapter 2. If you would like to test, you get the idea or not. Because one of the goals of this course also is when you watch some TV show or you listen to someone is talking about the experiment and these kind of things, you should be able to understand what they are talking about. So in this speech, you will find that Dr. Fauci was talking about some experiment that like in chapter 2. So you need to think about what he's talking about. He is talking about dependent case, or independent cases. What is the p-value? What is the null hypothesis? What is the alternative hypothesis? And what is the conclusion? These kind of things. So I will post an ungraded quiz about chapter 2 on our Canvas page in the new news section on the main page. And you can practice. There are only 10 questions, multiple choice questions, to see how much you understand the chapter 2. How much that when you listen to someone is talking about experiments or design of experiment, you are able to understand what is talking about. And then we need to practice on, as I said, when we finish chapter 2, I will go over the code, R code, and so on. So I will go over the R code with some real experiment data because we need to practice on R. I know I showed you the code, but let's do it together. And if you have any question, because some people are not familiar with R and these kind of things. Any question, guys? Any question? Okay, if you do not have any questions, thank you. And have a great day. I will let you know that the next class will be on Zoom or in person based on the situation. See if he fixes the problem or not. Okay, have a great day and see you.
Thank you.
Thank you.
Thank you.
Thank you. Thank you.
Thank you.
Thank you.